Hi, my name is Hugo. Today I'll be conducting a flight test briefing for the Albatros aircraft using a specialized Unity virtual environment tailored for simulation involving the Albatros aircraft. So first, the weight and balance. So the center of gravity is a critical factor in understanding the flight dynamics. Normally finding it directly without software can be a bit challenging. So in practice, we determine the center of gravity by measuring the reaction at the aircraft wheels. So here's how it works. So we place the aircraft on scales that measures the reaction. So we know the distance of the wheels related to the aircraft, and we know the forces. Thus, we can calculate the moment arm, and thus we can get the CG. Here we can change the value of the CG, and this will change the value of the reaction. So here we have again the center of gravity that we can change. So the distance of each wheels must be measured from a reference point. So in our case, the leading edge will be the reference point with a positive direction behind the leading edge. So here for the calculations, we have the position of each wheels. By changing the center of gravity position, we can measure the load for each wheel. From there, we can calculate the moment and the total moment. We know that the aircraft weighs 7 kg, so we convert it into a force. With the weight in newtons and the total moment, we can calculate the center of gravity. So we can compare with values that has been gotten from Unity and values from calculated CG, and we can see a correlation. However, the plot is slightly off. The best fit would be more straight and in the middle function like y equals to x. So next up is a thrust test. So to understand the thrust capability of the aircraft, we need to perform what is known as a static thrust test. So this establishes a clear correlation between the throttle settings and the resultant thrust. So the aircraft nose is secured against the scale right here, and if we turn on thrust, we can see the throttle given as a percentage of the maximum RPM. So this is 100% of 1000 RPM because it reaches 1000 RPM, and we have the thrust. The throttle is increased in increments. It's given here as RPM, and at each point we record the thrust. This allows to understand how the throttle input affects the thrust output, which is important knowledge for the pilot. So we need to verify that the aircraft respond correctly to the input controls. So we have roll right, roll left, pitch down, pitch up, yaw right, yaw left, and flaps down, flaps up. So here we can see that the change in trim angle of attack is consistent with the sign of the elevator input, and the aircraft pitch response is consistent with the change in lift on the tailplane. To determine the longitudinal dynamic response, we can record the changes in angle of attack. This is done for 3 different airspeeds and 3 different CG locations at percentage of mean aerodynamic core. We can see that the response is far more rapid at higher wind speed than the low wind speed. The oscillation is much smaller. It also changes with the CG. As the percentage of the mean aerodynamic core increases, the amplitude increases, making the aircraft unstable. So the most after CG position for acceptable pitch control of the aircraft is around 25% of the mean aerodynamic chord. The lateral dynamic response can be analyzed by looking at the roll rate. If we plot the roll rate with time for different air speeds, we can see with this figure that a higher airspeed implies a stronger aerodynamic force and hence a greater response for a higher airspeed. So additionally, we can plot the yaw response to cruise control. The yaw input changes the side slip angle. So we plotted with varying velocities again. So we can see that faster airspeed creates a faster dynamic response, as we can see with the green line. Furthermore, the effect of thrust line is very important. So if the thrust line do not pass through the center of gravity, changing the thrust can lead to moments about the center of gravity that will change the pitch, which is unwanted. So to analyze the flight performance, we can analyze the wind tunnel data from the Albatros, which is given by this MATLAB code. So in this analysis, we vary the angle of attack from -10 to 30 degrees. The lift and drag coefficient at 0, 15 and 30 degrees. The flap deflection is also recorded. The pitching moment coefficient is also recorded. And the elevator angles of -5 and 5 and 0. And we have 4 center of mass that are recorded at those values. So if we run the code, we get those values, those 4 graphs. So as we can see, the lift curve is plotted for each of the flap deflection angles. So increasing the flap angle will push the curve upwards. This is due to the additional lift, but this reduces the stall angle of attack. With no flap angle, the maximum coefficient of lift will be 1. Now looking at the drag polar. Again, drag polar is plotted for the different flap deflection angles. We can see the quadratic relationship that can be seen near the vertical axis. Looking now at the graphs below. So for the longitudinal trim, we have the pitch moments plotted for different elevator deflection angle. We can see here the yellow line here passes almost through 0, 0. This means that the moment is 0 at that particular CL. For the longitudinal stability, we have the pitch stability plotted here for different CG position. So if the plot is negative, the aircraft is considered stable, and if it's positive, it is not. So I would recommend negative plots. Testing the ground handling, this involves taxiing the aircraft so that we can verify the response to the controls input. So the maximum taxiing speed would be 25 meters seconds without the flaps. So this equates to 60% throttle. Beyond this value, the aircraft would take off. So the highest speed achievable in steady level flight is 45 meters seconds. So the lowest speed at which the aircraft can maintain approximately steady level flight would be at 22 meters seconds.